Alright, so I'm going to show you how to solve number 17 in section 1.2. So the question is, find the position function of x of t of a moving particle when given the acceleration. And then we're given the initial position and the initial velocity. So the main idea here is that we're going to integrate the acceleration function twice to find the position function. So for section number 17, we are given the acceleration function, which is a of t is equal to 1 over t plus 1 to the third. Our initial velocity is 0, and our initial position is 0. So first, what we're going to do is we're going to integrate v of t. Actually, we're going to integrate a of t to find v of t. So v of t is equal to the integration of a of t. And we just substitute that in with our main function right here. And since this is a little bit weird, we can use u substitution to integrate. So I set u equal to t plus 1, and my du is equal to 1 dt. So I set it up like this, and I integrate this u function. I bring up the u to be negative u to the negative third, because that just makes it easier to integrate. So then I add plus 1 to integrate and plus c, and then right down here is simplification, and then I move the u to the bottom just to have it more exact, and I bring out, I don't do anything else. Anyways, so you can substitute u back in. So we substitute in t plus 1, and I just brought this negative 1/2 out. And then what we need to do is we need to find c. So we plug in the initial v of 0 values, which were listed up here. V of 0 is equal to 0. So I plug that in, and I plug 0 into t, and then this is just working it out. This becomes 1 over 1. So that just becomes 0 is equal to negative 1/2 plus c, and then c is just 1/2. So then what you do is you plug that back into the velocity function, and then you have your full general solution for the velocity function. But we need to integrate one more time to find the position function. So that's what we do next. X of t is equal to the integral of v of t dt. So we plug in the velocity function we just found, and then what I did is I separated it into two parts to make it easier to integrate. So this first integration is negative 1/2 1 over t plus 1 to the second, and then I'm just integrating over here with 1/2. So you can also factor out the constants to just make it a little bit easier. So 1/2, I factored out the negative 1/2, and I factored out the 1/2 over here. So for the left side, what you can do is you can use u substitution like you did in the first part. And I set u equal to t plus 1, and du equal to 1 dt. And we don't have to do anything over here because we don't have to bother with that. So then I just did like I did in the first integration, and I moved the u up. I raised it to the negative power just to make it easier to integrate. So then once I integrate, I just add 1, and here's simplifying it out. So yeah, after that, you can move u to the denominator and then substitute u back in. So then we have, for our x, we have 1/2 1 over t plus 1 plus 1/2 t plus c. So we got to find the initial c value. So we plug in the initial position values to find the constant, which is x of 0 is equal to 0. So plug that in, and this becomes 0, and this becomes 1/2 is equal to, or 0 is equal to 1/2 plus c, and so c is equal to negative 1/2. So we plug that in to the x of t equation, and that's our general solution. And then if you want to, you can factor out the 1/2 to make it cleaner and more readable. So our final answer is x of t is equal to 1/2 1 over t plus 1 plus t minus 1. And that's how you find the position function from the acceleration function that was given.